Good evening mga lagan. We will continue with our design of one-story wood frame building. And this time we will be discussing the actual design of the structural members. We will design roof truss, floor truss, and then the wall studs, and then the beams on the mezzanine floor, and then the column supporting the mezzanine beams, and then different connectors from Simpson strong tie. And then the last one would be the lateral design, which is the diaphragm and shear walls and the accessories like hold downs if you have straps. So our design tools for today, design resources, we have 40 web. So we will be using 40 web for design of all the structural elements except the diaphragm and shear wall. So 40 web and Simpson strong tie. So for our design load, so we already calculated all the design loads in our previous video. You can check on that one. I think part 2A is dead load and live load and snow load, and then part of the funding load. Part 2B is the second half of the funding load, and then part 2C is wind load, and part 2D is seismic load. This is the summary of the loads that we calculated. So roof dead load is 30 PSF, and then roof snow load is 38.9, then floor dead load is 20, floor live load is 100. And then for the vestibule, we have this, it's no drift. So which is, this is 10 feet, or was that 10? Oh, 15, no, not 10, 15. So this is, that is 15 feet. And then the maximum is 130.3, and then the minimum is 70.18. And then we have the funding load. Now, if you remember our funding load, because we slope our trusses, right? We slope that way. And then we have our funding load here, like that. So basically what I did on this one is I just reversed the diagram. So this is the peak now, because that's the biggest load or the deepest water accumulation. So that would be the peak of your load, which is 56.78 PSF, and then at its bearing location, we have 4.78 PSF. So we will be doing a separate calculation for the funding and snow drift. So using 40 web, so we have this one here. So if you haven't signed up yet, you can sign up for a free account, and then you can practice this design. So the level we have, we'll just use the first one is a roof. Now make sure that, like I said in previous video, that when you open a new level, you have to select this one. Otherwise, you cannot select one. Once you start a design already, like you have a member here, then you cannot select this anymore. So you have to select this one right after you created the level. So if it's not residential, just use commercial application. Now to add a member, so on this one you have add members, this one add level, and then this one we haven't designed a member yet, but this is used if you want to copy a member. So this one, now since we are designing a roof truss, actually you can use these floor members if you design a roof truss or roof joist. The only difference is if you select this floor, the default load is for the floor. If you design the roof truss, then you select the floor. I mean, you can do it, but you will see here. So if you select a floor to design a roof truss, the only, I mean, you can do this, but all the loads are the default loads are for floor. Even the deflection criteria, see, if you select the code minimum, the deflection is 360 and 240. And then if you look at the loads, see, floor live, Although you can change this one, no problem. And then we have the concentrated load. And then if you use this selection floor instead of a roof, just make sure that this is zero. And then instead of floor life, you put zero there and then replace it with snow load. Going back, so we will delete this member because we are designing the roof. So add members, and then this time you select this roof, this one. So select that one, and then when I do a design, so for example, this is um, this is our floor plan, right? And then we have the vestibule. Now, what I typically do is for I have a like name for each member. So for example, this is roof truss one. So I will call this one R RT01. And then for the vestibule, we'll call it RT02. So the advantage of naming your member is for you to easily identify if you link the correct load. For example, you design the beam here or right here, and then you know that it is RT1 that is acting on that beam, right? So when you design this one, you can easily select when you link the load. I will show you that later to link the load, and then you will see the advantage if you name all your members. Before, what I usually do was I will just say, for example, usually you have a grid lines here, right? So you have grid lines here, and then say grid lines there, and then another grid lines there, and then I will say if this is A, B. I used to name them beam along A between say 1 and 2 if you have a beam here. So that's how I like the naming convention of like the element. But like later on I realized like it would be really difficult to find the specific beam. I realized that when I designed a what was the last I think it was a three-story apartment. And then imagine, I think there were 50 units total, I think. I can't remember. So imagine how many doors, how many windows along the perimeter, along the corridor. Now I should find another way to name all these members. So this is how I came up with this. So for example, if I have beam here, then another beam here, and then another beam here, and then I will use this one. If this is roof beam, then I will name it roof beam RB01, and then the next one would be RB02, and then the next one would be RB03, and so on and so forth. Now for the floor, if you have third floor, that is your roof beam, and then on the second floor you have your third floor beam. So on the level right here, on the level you can add one level here and call it now on this one we have mezzanine, right? So we'll add the mezzanine level, and then you can call it mezzanine beam one, MZ beam one, or MB1, or MB2. So it depends, like whatever is convenient for you to like use. So for mezzanine beam, like I said, you have MB01, MB02, and then if the beams are identical, then you can just call them both MB1 or MB2. But if there's a slight difference between the two, especially for like loading or span, then you can name them. And then after that, when you link the load, it is easy to identify which beam are you going to apply. So that is really helpful if you do it that way. and it's more like efficient. So let's design the truss. So our truss, remember our truss spans, let me add another page. So this is our floor plan. And then the roof, of course, at the top. So our truss spans in this direction, right? So we will have like that one, and then at the very end we will have um not the no, there is no overhang. Um so since this is flat roof with parapet, then we will have like an intruss here, that one. So this is 60 feet. That's the span, and then we will assume for now a 2 by 6 stud. We will finalize that one later, but the minimum would be 2 by 6, and then we'll check if the bearing is okay. If not, then we will add or we will increase the stud size. So for now, we will use the 2 by 6. So for the roof, so this is what the roof truss RP01. So that's the main roof truss, and then the lower roof truss for the vestibule is the RT2. Or you can have it like vestibule truss VT01. That's fine. So the member pitch. So for example, if you have a um gable roof, and then or a hip roof. So this is your truss, right? Like that one. Even if you have like a slope on your top chord, when I design, because this one is just to get the reaction and then apply, because you are not designing the actual truss. This is just like a mock-up design of the truss, so you will get the reaction and then apply that. Although you don't have to design the truss, you can just go directly to the design of studs and then apply the load as a like tributary area. That's fine as well. But when I do the design, I do it this way. So even if you have a slope on your roof, on your top chord, I will always assume this as a like a flat, no, like just a flat member, and then I will even assume like what are the possible member sizes, and then even if it fails, it doesn't matter because we are only after for the reaction. Going back to 40 web, so this one member pitch, I I just put here 0. And then it says here, flat roof recommended deflection criteria is L over 360 and L over 240. So that's fine. You'll just say improve. But it doesn't really matter because if this is a roof joist and you are the one sizing the roof joist, then this is crucial. You have to apply the appropriate deflection, appropriate slope. If the rafter is slope, then you apply the slope. But this one, the bottom chord, all the loads from top chord will be transferred to the bottom chord anyway, right? To the end, right? So you can just assume as like the truss as a flat truss. So that's fine. Unless you design an actual rafters. This is a pre-engineered truss. All you need on this one is just to get the reaction. Minimum load bearing for all point loads on the member 5.5. So spans and supports. Now this is the overall building length, right? Which is 60 feet or width or depth, whatever you call it. So this will be out to out. This one clear to clear. That would be uh, so if you select clear to clear, it would the dimension will be on the interior face of your support. But that's not our case here. So this is out to out, and then the span is 60. That one, 60. And then support one bearing length. So we already talked about that one last time. So if this is our truss, right? If this is our truss, then that's our parapet, bottom chord, like that. So right here we have a two-ply bottom plate or top plate and your stud. Now, if this is 2 by 6, your wrist size is what? 5.5. So this is 5.5. 5.5 and then 5.5. Now, this dimension location, since we are out to out here, then it would select like a left and right. And then if you select these custom dimension locations, for example, you can select this one. It's either at the center. See, it will move right here. But since we are out to out, we'll just leave it that way. And then this is grayed out because you cannot select that one because it is already out to out dimension. And then bracing, just say maximum allowable here for the bottom is bracing. But the actual design of this will be from the truss manufacturer. So all we have to do here is just a mock-up design of our truss so we can get the reaction and then link that load. Instead of the usual the tributary and then apply that on your wall studs, that's fine. That's another option. I mean, actually, I do that before, but since you can link the load, I decided, okay, we'll just do a mock-up design. It's easy. It's easy to do it that way rather than calculating that how many it will be carry every time you design the load. So we're done with the support here. So we have the type of the support. You have options of like beam, ledger, plate on concrete, plate on steel, bin plate, pocket, stud wall. Pocket is if this is like a you have a beam pocket on your concrete wall, something like that. And then plate on steel. So if you have a like a steel support and then plate on concrete, right? So for example, plate on steel, if you have a roof beam which is a wide flange section, and then at the top of that one you have to provide a nailer, then that's what your support plate on steel. If you have a concrete wall and then you have your sill plate, then you can select the plate on concrete. So for now, this is supported by studs, then it will be all studs. And then accessories, since this is a roof truss and we don't have rim board, but we have blocking, then you can select blocking. So when you select blocking, it will not subtract to your bearing length. But if you select a rim board, say 1 1/2 rim board, it will show here the rim board right here, and then it will subtract to your bearing length. You have to be careful with that one because if it happens that you selected that one a ring board, even if it is a roof truss and you only have blocking, and then you select a ring board, then it might fail on your bearing requirements. Now for the load, now this one RT1, this is using the snow. Because we will compare which one governs either the snow or the funding load, and then whichever governs, we will use that um, in the design of the other supporting members. So for the load, so your options here is you have point load if it is concentrated, or a point load PLF is if it is a concentrated load but in a like repetitive point load. If you design for example, if you design a beam that supports a truss, you can do a PLF or you can do a uniform PLF. So it's your choice. if the joints are really close to each other, you can apply it as a PLF. If not, then you can use the point PLF. I just use the PLF, like uniform PLF. And then uniform PSF, that is, it will ask you to apply or to input a tributary width. And then, of course, a tapered PLF if you have a tapered load. And we will be using the tapered load when we apply the funding load. So this is uniform because we are designing the truss, so we will be using uniform PSF. And then if your load is not like the whole length, for example on this one 60, and then your load is only up to 40, then you can uncheck this full length, and then it will update the loading here. So that one. But since this is the entire length of your truss, then we will check the full length. Now roof dead load is 30, and then the snow load is 38.9. So this is 12.53, and then the minimum, which is 5 at the internal pressure. So that is 17 point minus 17.53. So that is your wind load. That is upward. And then for the product selection, I will just use commodity lumber, and then two by SPF number one and number two. I mean, this is just a mock-up design, so it doesn't really matter. All you have to do is say in a truss you have a bottom cord and then you have a top cord, right? And if you want to get the actual dead load of the truss, um, like the truss member, then all you have to do is just use, say, your member is 2 by 6, and then on the spacing, even the roof truss are spaced at 24 inches on center, but because we are only calculating this for the purpose of getting the reaction, we'll just use 12. So you have a pounds per foot reaction. And then since you have bottom chord, 2 by 6 bottom chord, possible 2 by 6, then possible 2 by 6 top chord, and then 2 by 6 member, then just reply. So that's what I do. So I don't know, like with other engineers how they would do it, but I mean this is what I do with the design of trusses. I mean, at the end of the day, you are only after for the reaction, and then run the solution. So if you notice, all of this failed the moment, the liveward deflection, and total deflection. So it doesn't really matter. If you want to check the bearing, if you have the bearing, because when you submit this to the truss designer, and then they will design this, and then when you receive the shop drawing, in the calculation they will specify what's the minimum bearing length um, in their design. So to check that one, if a 2 by 6 will work on a single ply truss, that will be the minimum. Because if it's 2 ply, then that's fine. That's better because you have more bearing contact. But if it's only 1 ply, then you can also select this just 1 ply, and then just determine the reaction, the bearing. Now the bearing is 57%. So we are good with the bearing if we use 2 by 6 as our TAD. So after that, you go to report, and then these are the reactions. So these are the reactions. So your dead load is 900, your snow load is 1167, and your wind load is negative 526 pounds per foot. So that means that is uplift. So when you design the hurricane ties, this is what you will use. The dead load, which is 900. I don't know if you can see that one. So we'll just that one. So dead load is 900, and then the wind load is 526. Now for uplift calculation, you will use the point 0.9 dead load, and then Worst case on this condition is if there is no snow. So for uplift, you only account for the dead load and wind load because that's the worst case possible scenario. Because it's like you only have the snow during winter. So what if like usually here, the winds are really strong at during summer, and then there's no snow on that like in summer. So in uplift calculation, when you design the hurricane ties, you only use the dead load and the wind load. Now for load combination, we have here the principal load, which is this one load case 1.25, and then I think this is with crane, this one here. So you have 1.4 dead load and then 1.25 or zero point 0.9. This zero point 0.9, this is used for uplift calculation. You don't use the full dead load. So for downward, you apply 1.25 load factor, but for uplift, you apply a zero point 0.9. So you reduce the service load. And then you have here 1 live load, so we don't have live load. And then on the companion loads, if you notice, you have 1.0 snow or zero point 0.4 wind. And then another load combination is this one load case 4, where you have 1.25 or zero point 0.9, so this is for uplift, and then 1.4 wind. So if you look at all these load combinations, this one here, load 4, principal load, zero point 0.9 plus 1.4 wind, that is the governing load combinations on this one. So going back to our calculation, so we have our roof dead load is 900. How much was that? So we will use the combination zero point 0.9 D plus 1.4 wind. This is the governing load. And then dead load is equal to, what's that, 900? 900 um, kilonewton, or no, 900 pounds. And then the wind is negative 526. So wind is negative 526. Now, if you apply the load combination, so this is zero point 0.9 times 900, and then plus negative, so minus 1.4 times 526. So what is our uplift? So zero point 0.9 times 900 minus 1.4 times 526. So this is 73.6. That one, 73.6. And that is positive. So that means we don't have a net uplift. But you have to be careful when you calculate for this one, because this dead load, this reaction, this is just a like a rough dead load calculation. So it could be that the dead load, so we assume 30, right? Because when we design the member for gravity, we assume like the worst case possible like assembly, and that is assuming all the insulations um, are uniform, which is the thickest insulation at the very end. Because if we have the roof, this is flat roof, right? If we are the one, if the insulations are the one being slow, then we will always this maximum thickness here. But right here, it is thinner compared to the one at the very at the bearing location. So you have to be careful with uh, what dead load to be used. And to be safe, what you can do is just specify whatever is the least or the minimum hurricane tiles that you can find in the um, Simpson catalog. And I have here this is the old one, 2018. They have a latest. You can download the a PDF copy from the website, or you can go directly online and find the hurricane ties there. And then another one is yeah, this was given by the sales rep. He went to the office and give us all the design guides, the catalogs that we need for the products. And then every time they have a uh, new version, then they would send sometimes like during COVID, they just send it to us. Before COVID, the sales rep, Mr. Trivedi, he usually comes to the office. So if you don't have a like a hard copy of the connectors, you can go directly to their website. So you can go to their website and then Simpson Strong Tie and then find Hurricane ties. So you can use it's either this one, it's one or it's 2.5. We have lots of option on this one, and they have different of course different capacity. So I will typically use is specify if there is no or like very minimal net uplift, I will use the smallest hurricane ties. And let's check. They have each one. Um, for some reason, they updated their site, and usually it before it will give you the list of all the hurricane ties. I don't know. Let me check. We'll click this one here. Log tables. Yeah, they will give you the specific capacity of the hurricane ties. But before they have a long list of all the hurricane ties, and then you can just compare the capacity. Similar to this one here. So if you have the copy of their catalog, we don't have a net uplift, but you can use each one for this one. Product details. Uh, no, they don't have a image. So this is how the Hurricane Ties is installed. It's 2.5. So this is attaching a rafters. But if you have a truss, it will be the same attachment. Or if we select, let's see, we are choosing each one, the minimum. So each one Hurricane Ties. Where is each one? This one, each one A. I don't know where there's no each one. But yeah, this one, like a diamond shape. So this is each one. And then if you look at the image and video gallery and then installation, so this is how it is installed. So this is the truss here, and then this is installed like this one here. So that is each one a truss installation, right? That one. So this one it is reversed. If this is useful if you have a um like a continuous sheathing or something like that one, then you can reverse. It doesn't matter. Or if you have your bottom cord like flush with the edge of the top plate, then you can select that one, and then you can even install it on the interior side of your top plate. So yeah, so this one, so we will specify this one for our hurricane ties. So in the detail, in the detail, where's our truss drawing? Did we do a truss here? Oh, like this one here. So this is our hurricane ties right here, attaching the truss to the top plate. So next would be, if we go back to our plan, so we don't have beams at the back, so we'll just say design a beam. We will have a like an opening here, right? So this is a say 10 foot. Oh, so we have a 10-foot opening right there, and then I will show you how the loads are linked. So if we have the roof truss here above, no, supported by this opening. Now, if you draw the elevation, so this is your elevation, right? And then your window is right here. Now, unless you have a like full height window, right? But if just a regular window, it's only like few feet above the ground. Now, for the dead load, you have to assume or you have to include this weight of the wall. Because that's critical, especially if what if your wall finish is like stone finish or bricks. That's really heavy. So you have to consider the dead load of the wall above your header or above your beam. So um say this is 10 feet, the height of the wall above the opening. So when we design the beam, so when you design the beam, say that is RB01. We will add a new member, and this time, instead of a roof truss, this will be a roof beam. This one. It doesn't matter if it's a drop beam or a flush beam, that's fine. So this is roof beam RB01. Now, the minimum deflection is 240 and 180. So it depends on your finish. So if your finish requires more or like um, little tolerance with regards to deflection, you can use the improve, which is 360 for the live load and 240 for the total load. So it's up to you. Now for the span and supports, our window is 10 feet, but 10-foot opening is the clear because you have to consider. So, for example, if this is your window here, now this opening here, that's the width of your window is 10 feet, but our beam will extend past that opening because your support, your trimmers is right here, right? So that is where your trimmers are. So you have to consider that extra span of your beam. That's why in in Forte, when you input the beam span, you select this one as clear span, not out to out. Unless it is clear in your drawing that it is what do you call this one? It is out to out. But usually when you look at a architectural plan and it says there uh window 10-foot width and then say 7 foot high or 4 foot high. That 10-foot width, that's the actual width of the window. That's inside to inside of your support. So you have to consider that one. And then, so this is what? We assume 10, right? So that is 10. And then for the bearing length, so um you have to consider because right now this is not supported by a stud, but a trimmer. So this is you select this one as a trimmer. So the trimmer studs are the one right below the beam or the window header, and then next to the trimmer studs are the full height studs, which are called in post. And that is the full height one. So for example, in the in this opening here, so we have our wall, right? So we have our wall and then we have our window here. Now our beam is right here, right? you extend that, say, 3 inches or 5 inches or 6 inches um beyond the opening, and then you have your three mirrors. So these are your three mirrors here. These are the main support of your header. And next to that one, you have your full height studs next to that. And these are called in post. And then as well as right here. Now above your header, you have a stud, short one, and that is called cripple studs. The one above the opening, the short ones. And now this wall, this is the one that I told you that we have to consider that one, especially if the your wall finish is really heavy. So imagine if you have a stone finish or a brick finish that's really heavy. And then if you don't consider it one in your header design, then that's a failure. Unless it is clear in the analysis or in the drawing that it has a um another support or that is standalone. So if the bricks or the stone finish have separate support, then that's fine. You don't include those. Just include the actual like wall assembly, including the finish. So going back to Forte, so this is trimmer now, and then if you say the trimmers are two ply, so two ply that is 1.5 plus 1.5, so you put 3. But we'll see, maybe 3 will work. So we'll just, or 2 plus, so this is only 3 inches, and then this is also 3 inches, right? Because you have 2 ply trimmers. And then we'll see if 2 ply for the bearing requirements is okay. If not, then you increase the number of plies um, for the trimmers. So for the loads, we'll apply the wall above the opening. So the tributary height of that one, I think we said 10, right? So this is 10, and then oh, so that is 10, and then dead weight of your wall assembly, say maybe 12, right? 12 PSF. That's your dead load, and then now we will apply the reaction from the roof. So this is the time that you will link. Now, if you click this one, this arrow down here, you have quick loads and link reaction. So since we already calculated the roof thrust above, then we will use this link reaction. Now imagine if you have um, say 30 or 50 different trusses or different beams, and then you name it like beam one along or beam along A between 1 and 2 or between 2 and 3. So imagine. So if you name each beam, then it is easy to find. So our roof truss, this is RT01 snow, then we select that one. And then, so this is our truss diagram, load diagram. And then you select which, since this is uniform load, the load is symmetrical, the reaction is symmetrical, so it's either one or two. But if you have a varying load, you have to consider which support are you going to link, either support one or support two. That is crucial if your um, load is varying load. But this one, this is uniform load. The reaction is the same. Then it doesn't matter if you apply reaction one, because it says here choose the reaction to transfer. So it's either reaction one or reaction two. But in this case, we have the same reaction, then just leave it as one. And then the select type point load. This is if just one single load on the beam, right? But this one point load PLF, that is if you have a, like I said, if you have, say, your truss is every foot 4 foot on center, then you can use this one point load PLF. And then this one is the equivalent uniform load. See? So if you select this one, you are only going to apply a just one location. And then if you select the uniform PLF, then you are there's another dimension here, which is the end of your, if this is like the entire span, say if this beam is only, it's only like mid span, then you apply it from 0 to half, like, which is 5 foot 3 inches, half of your beam. But this is, since this is all the way, like the entire length of your beam, the entire span, then if you forget the span, then you just like hover on this eye here, this one, and then it will give you the beam that you are designing. So the overall length is 10 foot 6, this one here, the very top. So you input here 10 foot 6. And then placement top, front, back, then this is on top of your beam, then you select top on that one. Now, if you are not sure about this, the total length of the load, or the the length of the load application, you can edit it from here. Say if your load, say you decide, oh, the truss is only up to 8 foot of your beam, then you can update it here like that. But this is, since this is full span, then we will input 10 foot 6 in there. Now, if you notice the loading, the loads that you link, see, the dead load is applied automatically, which is 900, and then your wind load is 526, and your snow load is 1167. So this is that's why I, even if we are not the one designing the truss, I will still do the design of the truss as if I'm the one designing, just to get the reaction, and then it's easy to just link the load to the reactions. Otherwise, you have to apply the load um as a tributary area individually, like bid load, snow load. That's fine. But what if um your load is varying load? So it would be really difficult to, for example, imagine if you have a, like, next calculation will be depending load, and it is trapezoidal. So how are you going to select the, or choose the intensity, like the tributary area? That would be a tapered PSF, right? So that would be difficult. But if you design it this way, just do a, like a mock-up design of the truss, get the reaction, and link the truss itself, then in that case it is easier. So we already applied the load, and then product selection. So first we will just of course the dimension numbers are way cheaper than engineered wood. So your first attempt should be dimension number, unless the owner or the contractor wants a, like an engineered beam design for this particular header, then go directly with the engineered beam. But when I do design for, like, for any project, I will always start with dimension number, because that's way cheaper than engineered wood. So two by this one, two by SPF number one, number two, and then say we'll use 2 by 10, and then two ply. We'll say two ply first. Now it fails here, right? Everything is red. So all you have to do is you go back, and then the biggest or the largest dimension number that you can buy from, say, Home Depot or um, Home Hardware, it is 2 by 12. Now this one, you have one ply, number of plies. You only have four plies as the maximum width, but If we select 4 ply, so each ply is 1.5. So if you select 4 ply, so 1.5 times 4 is 6 inches. But you have to remember that you select a 2 by 6 stud. So a 2 by 6 stud is only 5.5 inch wide. So if your stud is 5.5 inch and then your beam is 6 inches wide, then it will not flush with the stud. So you have problems there, right? So all you have to do is say your limit would be 3 ply. So let's try 3 ply 2 by 12. Still it's failing, right? So we have no other options but to use a like an engineered product. So this time it's either microlam LVL or paralam PSL. So paralam PSL, it's a good option if the beam is exposed and you want a cheaper version of a like an engineered wood beam. If you want the expensive one, then you can select the glue lamp. So this one, like LVL, it's not really good looking. Like the surface is not nice to look at. If this beam will be hidden in a drywall, then that's fine. You can select LVL. But since this is inside a wall, then that's fine. LVL is fine. So there's only one width for LVL, but Paralam have different width. You have 3.5, and then 5.25, and then 7 is the widest beam. But you have two different modulus of elasticity. One is 1.8, and then the beam application is 2.2 E. So that's the modulus of elasticity. That's stronger and um, good for if you have like a issue with the deflection of your beam. So we'll check LVL and then say 1178, and then we'll go directly with 3 ply because the bigger the beam, the more expensive it is. So our maximum is 3 ply again because 1 ply of LVL is 1.75, and then 3 ply is 5.25. So ano, 1.75, that's the ply, and then 5.25, that's 3 ply. And then our stud is 5.5, so it fits within our stud. So 3 ply 1178, and then hit solutions. Now our bearing is 97%, and then our shear is 62, our moment is 90, and then live load deflection, it's good. L over 604, our actual is 0.2, and then allowable is 0.3. So we are good with this beam. Now, with regards to bearing, if you are not comfortable with this 97%, or worse, it failed, all you have to do is just increase the number of plies for your trimmers. That means instead of just 3 inches bearing length for your beam, it will now be 4.5, like 3 ply. So if in case this bearing here fails, then all you have to do is increase the bearing length. So if this is 3 ply, this will become 4.5. Now, if you notice, the load 10.9 is a little bit short from your beam span because we added that 1 ply on each side. So you have to consider that one. So you update the load as well. Now the overall length now is 10 point or 10 foot 9 instead of 10 foot 6. Then just change this to 10 foot 9, and then go directly to solution, and then see, now this is 66%, right? Now if you think like we have so much extra capacity on your um building, your other option is either instead of 3 ply just use 2, and then we'll see. Oh, it fails in bending and deflection. So we have to use 3 ply. But what about um, a shorter one? Instead of 11.78, we'll use 11 and a quarter LVL. So we are 99%. So if you are comfortable with 99%, then go for it. If not, no, you might say we have to include there's another factor in design, and we call it the factor of ignorance. So to consider the factor of ignorance, you will add a you will increase the beam to the next size, which is 11.78. If you are not comfortable with the for example, how much was that? 99%, right? So if you're not comfortable with 99%, then all you have to do is just upsize that one. But if you are comfortable with that, especially like if you go back to your how much load did you assume, and what are the possible or what are the chances that the load will be lighter than what you assume, then you can leave it like that. But the LVL, I think the most common LVL, the minimum is 11.78 anyway. I mean, you can get 7 and a quarter or 9 and a quarter LVL. You can get those sections, but I think the most common is 11.78. So so we already designed the beam header. Now this is considering snow. So this is RB1, which is using the roof truss with snow load. So what about the funding load? So we'll compare now which one governs. And then if the funding load governs in the overall design, then we will use it, you will use the funding load as the the truss, like the design for all the structural elements. So roof truss 01. So we will copy this one. So this one, copy member. So like I said, you can use this one if now we have the same trust. The difference is only the load. So we don't have to update all the load, the span again, the bearing again, right? So all you have to do is just copy this one and then rename it RT01 and then funding, that one. So RT01 funding. So then all the beam informations are already done. All you have to do is go to the load, and then your dead load is still the same, and then you have the uplift, but you have different snow. You don't have snow, but you consider the funding. Now, in this calculation, what you can do is since we are only after the load, compare basically which one governs snow or um depending, but this load here is uniform PSF. So all you have to do is delete this snow here, delete this snow, and then you add another loading. So another load, that one, and then this time this is tapered PLF. So this is tapered PLF because if you remember our load, this one, our pending load, this one. So this is tapered. We have the deepest water accumulation at the center of the truss. So we have this 56 from 4.78 to 56.78, and that is PSF. Now, since we space our truss at 12 inches on center, so we can consider this one as 1 foot tributary. Then this is our loading. Otherwise, if you use a 2 foot spacing on your truss, then you have to multiply this load by 2, considering the tributary. That's why when I select the truss, when I select the spacing, I only selected 12 inches instead of the actual spacing, which is 24, so that all the loads will be 1 foot tributary width. Then whatever is the load, that's the load. You don't have to multiply it. So going back to the calculation, so this is full length or no? So this is not full length because our peak is at the midspan. So the midspan is 30, and then your ano, yeah, 30, and then not full length 30, not uniform. This is tapered. So your location is from 0 to 30, and then your now this time we don't there's no option for panding load, but the load factor for panding is also 1.5, which is the same to your snow load. Then just use just use the snow load um for the panding. So this one is 4.78, and then the maximum at the end is what's that, 56.78. So this 56.78, that one. And then see, so it changes the load diagram. Then you have another load. Just copy this load, and this time this is opposite. So this is 56.78, and this is 4.78, and then this is from 30 to 60. So this is 30 to 60. So that is your total load diagram. So that already includes the uniform load, which is dead load and wind load, then plus your funding load. Now we will compare this one, which one is um which one produce the biggest bending, biggest reaction. So let's check. But since we are only after the reaction, so we will compare the reaction only. Product selection the same. So for solutions, our member reaction here is at 49%. That's the utilization ratio. The actual reaction is, the factor reaction is 2,510 pounds. Now, if you compare that with the snow, 2,510, the snow is 2,876. So therefore, it is the snow load that governs in the design. So you choose that one. So we are good with this one here. So this one pending, you can disregard that one. But on the vestibule, you have to be careful because sometimes we had, I think, uh, two or at least one project that I can remember. What they did, that's why if this is the case, you have to tell the mechanical engineer to relocate the downspout, because what happened on that project. So I will explain it to you. So this is, you have to be careful with this one. So what happened, this is the higher roof. And then in this case, especially we have vestibule, so we'll just say like that one, lower roof. But the mechanical engineer designed the roof so that the any water here, like the downspout, is connected to is the outlet of the downspout is on the lower roof. Now, if that's the case, all of this water here will be applied to this one when you design this um when you design the panding load for the vestibule. Now, if you have, for example, you have a parapet of like really high parapet, right? So imagine, and then or your location of your scupper is really high. So there's a possible like it will be like a swimming pool, swimming pool on top of your lower roof or vestibule. It happens in one of our project, at least one that I can remember. So I told the mechanical engineer and the architect like can we relocate this one because this produce a really high like funding load, and they said no because it would change the overall like aesthetics of the building, and said okay, if that's the case then I have no option. So I designed the lower roof like with the like really high funding load, and yeah, so you have to be careful with that one. You just don't design um, for the funding load considering the tributary only, but you have to consider if is there any other ground spot that is feeding that um, funding load on the lower roof. So you have to be careful with that one. So going back to the design of, so we already sized the beam. Now this one, this is final now. So this is the final beam. RB1 is no, because that is no governs in the calculation. So again, the total reaction for funding is only 2,510 versus the snow, which is 2,876. So the snow load governs in this particular design. So this one here. So we are done with our roof truss and then pass to the beam, and then we will check the trimmer stud. So we have a three-ply trimmer stud. So if you go back to, so again, this one here, and then if you go back to, or you add a member, if you notice here on the wall, we have this feeder, and then we have this window sill, and then we have this stud, like the uniform wall stud, uniformly spaced studs. And then we have this single um, wall stud, wall column, this one here. So we will select this one and use this as the use this for designing the trimmer. So say this is trimmer 01, right? So that is trimmer 01. And then if you want, you can say trimmer 01. This is supporting RB1, so RB01. Or you can have, you can name this like this one here, trimmer 01, and then open close parenthesis RB01. So it means this trimmer 1 is supporting RB01. So, or you can have just T01 only, T02, whatever. So that's fine. But these are the following the different way of naming the member. So your height, so say your height is, it's not the overall height, but this is underside of the beam. So say the height is 10, or whatever is the height in the plan, but say that is 10. And then the plate size top is, so the plate size is double 2 by, and then the base is single ply 2 by. So if it's 2 by 6, then 2 by 6. If it's 2 by 8, then 2 by 8. And then the plate material, since we are using SPF stud, then this will be SPF. Then parallel to wall bracing. Now, if you're bracing, because this one here will determine the capacity based on the slenderness ratio of your slenderness ratio of your stud. Now, since we have sheeting, right? If this is an exterior wall, then we have sheeting on the outer side. Then this one, instead of fire blocking, you use the wall sheeting. Now, if this is full height without any, without any blocking, then you can use the full member height. Or if there's a specific spacing, say every 3 feet, every 4 feet, then you can select this custom. or just because we have sheeting, then you will use the sheeting and then um 12 inches on center because that's the maximum spacing for your field nailing when you decide when you attach the sheeting to the um studs. So that one. Then loads. Now on this one, we our only load here is the reaction from the beam. So we will link the reaction, which is this one RB01. And then which reaction, it doesn't matter because this is symmetrical. Then we'll just use R1. And then since we don't have this load anymore, we can delete this. And now the eccentricity for vertical loads. Now, as a minimum, you can select this 1/6 side of side dimension or center of section. So it depends on like the what we call this one, the placement of your supported member with regards to the supporting member. So we have center of section, edge of member. If you have a, like say, if you have a column and then your beam is face mounted, then that is edge of member. So for now, we'll just use this one here, 1/6 of side dimension. That's the minimum. So on the product selection, commodity lumber, and then 2 by SPF number 1, number 2, and then we say this is 2 by 6, right? So 5.5, and then 3 ply, yeah, standard orientation. So if you look at this one, it failed in gearing. So 108. So it failed by 8%. So if you are comfortable with this one, then just leave it as is. If not, what you can do is increase the number of ply. So if you increase the number of ply, so it is fine now. So plate bearing, it already passed 81%. So our final design would be, we have a beam and then 4 ply reamers. Now for the mezzanine, so we already designed this, yeah, like in our last video, but we will just do it again because I deleted I deleted the calculation. So add members, floor truss, ano, see, I forgot to change this one, residential. So you have to be careful. So we will delete this first. So we will delete that first and then um select the commercial right here. So commercial and then add floor joist and then we have, so for a floor joist, say if J01, since we have the same like uniform like joist, will just call it FJ01. If you have different joist like different span or different orientation, then you rename it with you name it with other. So on this one, span was what, 30, but this is out to out, right? And then this one, this is a 2 by 6, so 5.5. And then this time we have a ring board. And then typically it's 1 1/4 ring board, LSL. If that is engineered wood, then use LSL 1 1/4. If this is our choice is a dimension lumber, then you have to be careful with this one because if that is a 2 by 12 joist, then you have to use also a 2 by not necessarily, but if you are using a dimension lumber for your joist, then use the same for your rim board. So you have to select a 1 1/2 rim board. So since we are using engineered joist, then we'll use engineered rim board also. And that is 1 1/4 LSL rim board. And then on the other support, this is where the beam is. So the beam, this is face mount, and then this is beam. The beam is LVL, and then we'll say 3 ply. So just leave it as 3.5. And then the load, The load we have 20 dead load, and then floor live is 100. Uniform PSF, and then our concentrated load is 2000. So our span, again, this is out to out. And then product selection, we use TGI 560 20-inch, and then was that 16 inches on center or 12? I think 12. So again, it takes time because we have that concentrated load, and this is 30 full span, so you have at least maybe 30, 20 to 30 iterations. So it failed in, I think we use 12 inches on center. So 12 inches on center. Now we are failed with our deflection, but this is L over 420 because we are using a like the improved deflection criteria. But if you use the code minimum, because there's nothing special with this one, unless you have a really sensitive equipment above, then you can use the code minimum. Then this should be fine. So yeah, let's wait again. So we are good with our joist now. So our joist is um, TGI 560 at 20 inches, TGI 560 at um, 12 inches on center. And then our joist hanger is this one here. I don't know why this is. We'll check top mount because that's a heavy joist hanger. Um, we'll check this one will be top mount, and then we'll see. So for top mount hanger, yeah, this is more like this is like a regular joist hanger. It's be 3.56 20. So we will use a top mount hanger this time. I don't know why in the last video we had it as LF something, 23 or something. But yeah, this time we will use HB 3.56 20 um, um, hanger. So to give you an idea, HB 3.56, what it looks like. So you just search in the job strong tie website. So this is what it looks like, the joist hanger. Where is it with that one? Oh, this is 5.5, 16. But it would be similar to this one here. Because we are using 3.56, 20. And then these are different, maybe this one here. See? So it will look like that one. So we already have this, we designed the roof truss, the studs. Oh no, we haven't designed the studs yet. The beams and the trimmers, now the floor joist. Now we will design for the beam. Now for the mezzanine beam, going back to our floor plan, so our mezzanine is, we have 20 feet, 20, 20. So our beam span is 20 feet. Now, assuming we will use a, for the column, we will use a wood column. So we can show it, I can show it to you here how it is done. And then we'll just use a column cap. So for now, our beam is 20 feet. So our beam, we have add new member, floor beam. So this is, say, this is in beam, mezzanine beam, 01. Now, if you remember, we have on this one here, we have a beam that is supported by a, like a built up post here at this end, and then another one with a column cut. So we will make this one as MB1, this one here, MB01, and then the one with both column cup at its end will be MB02. So we can differentiate the two. So, and then also to give you like when you link the load, and then you can find which one are you linking. So in B01, this is the one with one end supported by a built-up post, and then the other end would be a column, first standing column. So in B1, this is now this one. If you remember this one here, the column here would be like the 20 feet will be the center of column. Now, we will consider that in our analysis. Though this time, we will use the custom dimension where the left one would be using the left, so the outer one, and then the support will be center because we are center of our column. Now, our column cap, say the column cap is now if you look at the different column cap, say CC 66. Now this column cap here, the length of this product details or image, maybe it's right here, illustration. So this one here in the table you will find this length. So if remember, if you whatever is the required bearing length, you multiply it by 2, then that would be the minimum length required because you have to um column on each side of your column. You have two beam on each side of your column. So it will be, so whatever is the length here, or whatever is the minimum bearing length required when you design the beam, and then multiply it by 2, that's your length required for your what we call this one, your column cap. Or you select a column cap and then input the load and then use the half of the length. So for example, our column cap is 11 inches in length, like the bearing length. So half of 11 is 5.5. So let's go back to our, going back to our 40 web. So this one, this time this is a bottom and then stud wall. This is column cap. Now, if you notice this one, our column cap, it is drawn like that one because there is no continuous. If the beam is continuous, like over two span, then you will add this span 2 here. So this is 20. And then span 2, say 20 also. So right here. So and then if this is center, then like that. But since we only, this is a single span beam, then we will use that one. Now, if you notice these two here, if you assume a bearing length of 11, if you input 11, then it will the 20 foot will be at the half of the 11. But for this one, we will use the outer, or just out to out, and then this one here instead of 11, that's your total length of your total bearing length of your column cap. Just use 5.5, that one. And then right here, this is 2 by 6, so this is 5.5, this one. And then we'll check first if it will pass using just a stud wall. Otherwise, if it fails, then all we have to do is just change the stud wall into a trimmer, because it's stronger that way. Because you are bearing perpendicular to for a top plate, the bearing is perpendicular to the grain. But if you are using a trimmer, it is parallel to the grain, which is much stronger. So on this one here, still, so we're good with this one. And then for the loads, now our only load is the joist. So delete this one and then link the joist, this one, if J01, and then it is uniform. Now this time you have to select this time, because the joist, one end of the joist is bearing on a wall and the other one is a joist hanger. Then this is the time that you select the actual reaction to transfer. So this is one, this is two. So we are designing the beam, then we select reaction two, and then uniform PLF. The total length is 20, and then front side or back side, whichever you select, but not the top. So that one. So yeah, we apply the load, product selection, we'll use LVL, and then our joist is 20 inches, right? 20 inches depth. Then we will try to design it like a 20-inch LVL as well, so that it is flush. So we'll select 20, and then we'll say it is 3-ply. So it failed in bearing, in bending, and then live load as well. So we will see if a 4-ply 24 is fine. So we failed in bearing. Now this bearing is at 4 inches, right? So it means it failed in reaction 1, right? Your support 1 failed due to insufficient bearing capacity. Now if that's the only failure, let's check what else. 37. We'll see if 4-ply 20 will work for the bending and deflection. Yeah, so this time the 4-ply LVL 20-inch is fine with except the ring. So we will try to change the support at 1, change it to a trimmer, and then that means that your your plate will be cut at the beam location, so that you have a full height post directly underside the beam. So we'll see what will happen. See, now the bearing is 67% versus the 113% bearing. So because if you use a stud wall, the bearing the bearing capacity will be based on the uh, perpendicular to the grain. But if you have a trimmer, then it will be parallel to the grain, which is way much stronger than the parallel one. So that's why on this one we are good with 4-ply 20-inch LVL, and then on the other end would be column cap. Now we will do the same for the one in the middle with both column cap. So we will just copy the member, and then name this in B02, and then the load is the same, but the span will be different. This time it will be the same as both column cap on its end. So this is also column cap, that one. There's not much difference on this one, but I just want to show you, like, um because when you link the load, when you design the column, it is better to link the actual configuration or actual support of your beam. So for sure it is fine because we only failed in bearing on the top wall, but since we are both column cap, which is steel, then that's fine. So the reason why I name it MB1 and MB2, so that when we design the end wall column for the beam, so we will have um, say new member and then wall column. This time this will be, we will call it C01. So C01, and then the height would be say the same 10, and then top plate, double top plate. So this one, we'll just leave it like that. So this is 10, and then this is sheeting, and then the loads will be from the MB01. MB01, which is reaction 1, that one there, delete this one, and then product selection. So our beam is 3 ply LVL, so that is 5 1/4. Then we will use 4 ply 2 by 6. So let's see if this is okay. 4 ply 2 by 6. So it failed in bearing. So the bearing here would be at the, yeah, your bearing plate. Let's see this one here. This is engineered wood, PSL. We'll just select PSL on this one at the top, and we'll see if the one that failed is the one below the bottom plate. So it failed in bearing. So what we can do here is we can have a bearing enhancer, or other option is we will cut the bottom plate and have this stud directly sit um on top of the foundation. So that's your only option. Otherwise, you have to use an engineered column or engineered post in post. We'll see. Let's try. Check. Let's check if if this one is Paralam PSL. This one 5 1/4 by 5 1/4. That one. Let's see if it will see the same. So the problem here is really the bearing at the bottom plate. So one way to support this one is either have some kind of a bearing enhancer at that steel plate, so it will distribute the load, or cut the bottom plate, have your input sits directly on top of your foundation. So that's your only option, because we have no problem with other criteria here for the shear, for the compression, slenderness. We're good with that. We are just feeling in the bearing. So now next is the interior column. So the interior column is a freestanding column. This one here, because we don't have walls. So you have to select this one, and let's call this one as C02, and then the height is 10. Now the type, the display type is um, steel, or you can have like a post base, which is I mean recommended, because unless this is like a what we call this one pressure treated and then sit directly on the foundation, but you have to provide some kind of lateral restraint. But if you use a post base, it will protect your column. You don't have to use a pressure treated column, and then it has also a lateral resistance. So we'll just use the post base, and then the load would be Now this time, our load is from MB01, which is, or MB02, if you want, or MB01 and then reaction 2, right? And then the next one is the other beam. The other beam is MB02 and then either one of the reaction to transfer because these are the same. And then product selection, most likely this will be an engineered wood. So Parlam PSL, say 7 inch by 7 inch Paralam PSL column. So that is okay, but we have a lot of extra capacity. So maybe we'll use 5 1/4 by 5 1/4. Then we failed in compression and like the interaction. So therefore we have to use at least 7 by 7 Paralam PSL. Or if you want, you can use an engineered or no a steel column. That's fine also. So now if you notice our reaction is 53 53,635. So that is our compression. Now we will find the actual or the proper column cap on this one for your column, attaching the beam to your column. Now our column is 7 by 7 and then our beam is 4 ply. So we have so our column is 7 by 7, so 4 ply LBL. So 1 3/4. So 2 ply is 3 1/2. So therefore this is the total is 6 inches.
Total
And then
should
your
be
post would
7
be
inches, not 6 inches.
7 by 7. So that is your cross section. Now we will find a column cap for that one. So let's check. I will just go directly here because I don't know the unlike the catalog where it has a list of um different column caps and then different capacity. Otherwise, will if we go online, it will be like a for a particular product only. So we will use column cap CC. So 7 column is 7. So W2 should be 7, at least 7. So we have 7 and 1/8 W2. Then W1 is should be at
Total should
least
be
6.
7 inches, not 6 inches.
So we have CC 7/8. So this is your column cap, and then like that one there. So if you look at the elevation, it would look like this one. So this is your beam, and then this is your column, and then that's your splice, and then this one would look like this. That one. Um, so this is your column cap, and then your leg here, and then you will have your bolt, and then fastener as well here. So that's what it looks like. And this is C78. So CC78. So when you call out this in your detail, you say Simpson CC78 column cap, right? So CC78, the 78, the W1 is 6 1/2. So this width here is 6 1/2. This is also six
Total
inches.
should
Then
be
we have
7
extra half
inches,
inch.
not
Then you
6
can assume
inches.
that whatever the extra clearance because there's no 6 1/4 or 6 1/8. And then that one is good for CC78. The factor normal resistance is 58,000 970. So 58,970, that's the rated capacity for the column cap. And then our actual reaction is 53,000. So we are over the um, load, which is we have 58 for the capacity, and then the actual is only 53. So I guess we're already 2 hours. So we will just continue the other elements. So we are already done with the roof truss, right? We are done with the roof truss, and then we are done with the floor truss, wall studs. Oh no, we haven't done the wall stud yet. So we have to do this one in the next video. We're done with the beams. We're done with the columns, and then we haven't done the vestibule part. So we will do the vestibule also, considering the snow drift, and then for sure it will with assuming that the downspout is not discharging into your onto your vestibule, then we can say that the governing load on that one is the snow drift is really high. The snow drift is really high at the vestibule location. And then next would be the diaphragm and shear wall design. So subscribe and see you on the next video. Goodbye mga lagan.